Good morning, sir. Good morning, classmates. My name is Javelisa Troncoso, and together with Ma'am Kim Bridget Osaraga, we will be discussing the parallel databases, hardware, and software. The outline of our topic are the following: the goal of database management system, need of parallelism, the goal of parallelism in databases, parallel database architecture, virtualization on multi-core processors, software and hardware parallelism. So let us start with the basic goal of database management system. So what exactly is the goal of database management system? So when we say database management system or DBMS, so it is a collection of programs that enables users to create and maintain databases and control all access to them. No, so the primary goal of DBMS is to provide an environment that is both convenient and um, efficient, no, for users to retrieve and store information. So with the database approach, so we can have the traditional banking systems as shown in this figure. So in this bank example, so a DBMS is used, no, by the personal department, the account department, and the loan department to access the shared corporate database. So what exactly the importance of database? So a database system stores essential data about a business or organization. So the data, when analyzed, becomes valuable. No, becomes valuable information about a company and helps in the decision making. So likewise, a database helps now build an archive about the business or the organization. So making a company more robust and aware of where it's headed when making choices. So storing data about an interaction helps provide insight into information to help the company develop further and increase profits. So databases are growing increasingly large, and large volumes of no transactions data are collected and stored for later analysis. And also, multimedia objects like images, no, are increasingly stored in databases. So the large scale parallel database system is increasingly used for storing large volumes of data. Second, processing time-consuming decision support queries and providing high throughput for transaction processing. So parallel database system seeks to improve performance through parallelization of various operations such as loading data, building indexes, and evaluating queries by using multiple CPUs and disks in parallel. So parallel machines are becoming quiet, common, and affordable. So the prices of microprocessors, memory, and disk have dropped sharply, and the recent desktop computers feature multiple processors, and this trend is projected to accelerate. So companies needs to handle huge amount of data with high data transfer rate. So the client server and centralized system is not much efficient. So the need to improve the efficiency now give birth to the concept of parallel databases. So, parallel database system improves performance of data processing using multiple resources in parallel, like multiple CPU and disks are used parallelly. So, it also performs many parallelization operations like data loading and query processing. So, the concept of parallel database was built with a goal to first improve performance. So the performance of the system can be improved by connecting multiple CPU and disks in parallel. So many small processors can also be connected in parallel. Second is to improve availability of data. So data can be copied to multiple locations to improve the availability of data. So for example, if um, if a module contains a relation, yung kanang table sa database, so which is unavailable, then it is important to make it available from another module. Okay, so third, we have improved reliability. So reliability of system is improved with completeness, accuracy, and availability of data. Fourth, provide distributed access of data. So companies or organizations having many branches in multiple cities can access data with the help of parallel database system. Okay, so talking about the parallelism in database, so we are accessing um, most large volumes of data through parallelism. So data can be partitioned across multiple disks for parallel input output where anytime we can read and write multiple disks. So database parallelism is a method of implementing parallel processing in a database. So an attempt to increase database functioning in a short period of time. So parallelism in the database covers all the operations that are usually going through in a database, like kanang magload sa data, transforming the data, executing the queries, and etc. Concurrently. So this helps to improve data consistency, system performance, parallel access of data by making use of multiple data sources, multiple systems memory usages, multiple disk space occupation, hierarchical flow with lesser time spent compared to individual process execution. So in this example, dito sa ating figure, so we have an example of database, kaninga figure. So we are talking about large, okay, volume of data. So in the data, if the data is very high, okay, so that particular relation can be partitioned in many disks. No. So once a relation has been partitioned among several disks, so we can retrieve it in parallel using all the disks. So similarly, when a relation is being partitioned, so it can be written to multiple disks in parallel. So the transfer rates for reading or writing an entire relation are much faster. So as our example earlier, so data can be um, partitioned in various disks and every process is assigned to it. So in our example, so we have a large volume of data that is partitioned in different disks and each disk has its processor. So we have here three processors. So we have P1, P2, and P3. So each processor are accessing simultaneously the disk 1, disk 2, and disk 3. So thematically, the work is distributed and the work is in parallel. Simultaneously, each process is working. So in parallel database machine environment, so instead of a single backend, so there are multiple backend machines connected either to a single host or to multiple hosts. So the back end control multiple disk units containing the database. So there are many opportunities for parallelism in relational database management system, and we have three main architecture of parallel database. We have shared memory, shared disk, and shared nothing. So in a shared memory architecture, the processors and the disk have access to a common memory. So typically via a bus or through an interconnection network. So the benefit of shared memory is extremely efficient communication between the processors. No, data in shared memory can be accessed by any processor without being moved with software. So a processor can send messages to other processor much faster by using memory writes, now which usually takes less than a um, microsecond only. So then by sending a message through a communication mechanism. So the only downside of shared memory machines is that the architecture is not scalable beyond 32 or 64 processors because um, the bus or the interconnection network becomes a bottleneck since it is shared by all the processors. So adding more processors does not help after a point since the processors will be spend most of their time waiting for their turn on the bus to access the memory. So shared memory architectures usually have large memory cache at each processor so that referencing of the shared memory is avoided whenever possible. So however, at least some of the data will not be in the cache. So in the cache and accessing will have to go to the shared memory. And moreover, the caches need to be kept coherent. That is, if a processor performs a write to a memory location, the data in that memory location should be either updated or removed from any processor where the data are cached. So maintaining cache coherency becomes an increasing overhead with increasing numbers of processors. So consequently, shared memory machines are not capable of scaling up beyond a point. So current shared memory machines cannot support more than 64 processors. Next, we have the shared disk system. So in the shared disk model, all processors can access all these directly via an interconnection network, but the processors have private memories. So there are two advantages of this architecture over a shared memory architecture. So first, since each processor has its own memory, so the memory bus is not a bottleneck. Second, it offers a cheap way to provide a degree of fault tolerance. So if the processor fails, the other processors can take over its task since the database is resident on disks that are accessible from all processors. So we can make the disk, no, we can make the disk subsystem itself fault tolerant by using a RAD architecture, no, as discussed by our previous reporters. So the shared disk architecture has found acceptance in many applications also. So the main problem with a shared disk system is again the scalability. So although the memory bus is no longer a bottleneck, the interconnection to the disk subsystem is now a bottleneck. So it is particularly so in a situation where the database makes a large number of accesses to the disk. So compared to shared memory system, the shared disk systems can scale to a somewhat larger number of processors, but communication across processors is slower, no, since it has to go through a communication network. Third, we have the shared nothing disk system. So in a shared nothing system, so each node of the machine consists of a processor, okay, a processor, memory, and one more disk. So the processors at one node, okay, may communicate with another processor at another node by a high-speed interconnection network. So a node functions as the server for the data on the disk or the disk that the node owns. So since local disk references are serviced by local disk at each processor, the shared nothing model overcomes the disadvantage of requiring all input-output to go through a single interconnection network. So only queries, accesses to non-local disk and result relations pass through the network. So moreover, the interconnection networks for shared nothing systems are usually designed to be scalable so that each transmission capacity increases as more nodes are added. So consequently, the shared nothing architectures are more scalable and can easily support a large number of processors. So the main drawbacks of shared nothing systems are the cost, no, of communication and of non-local disk access, which are higher, no, than in a shared memory or shared disk architecture, since sending data, no, involves software interactions at both ends.
Okay, let's continue with virtualization on multi-core processors. So the processing power of the computer is of course increased by adding many CPUs. So this technique is referred to as the virtualization. Okay, so multiple CPUs are added to the host machine, which can improve the performance of the system. So there is no specific rules for adding number of CPUs. Multi-core processors have the ability to solve complicated processing. So this technique is used for heavy load process. Now let's discuss about the two types of parallelism. So we have hardware parallelism and software parallelism. So hardware parallelism refers to the type of parallelism defined by the machine architecture and hardware multiplicity. So this means that hardware parallelism is mainly working on the machine architecture as well as the hardware multiplicity. So it's how the hardware parts are going to be connected so that the instructions can be executed but in a very less time. So hardware parallelism is a function cost and performance trade-offs. So it displays the resource utilization patterns of simultaneously executable operations. So it can also indicate the peak performance of the processors. So, um, One way to characterize parallelism in a processor is by the number of instructions or instruction issues per machine cycle. So this is the main concept of hardware parallelism. So it can be characterized means that's going to be designed completely based on the number of instructions that can be um, issued per machine cycle. So that means for each machine cycle, how many numbers of instructions this hardware parallelism can support. Okay, so if anyone's familiar with pipelining, this refers to fetch, decode, execute, and write memory. So we can consider each and everything as an issue. So fetch the data from the memory, decode the data, doing arithmetic or logical operations, execute the logical and arithmetic operations, and then write the result back to the memory. So each of these issues can be executed. In parallelism, multiple processors can execute multiple instructions. So here we have number of instruction issues. So let's assume that we have three instructions. So one is arithmetic, one is memory access, and one is branch instruction. So three issues per machine cycle means per clock cycle. So they can do these three instructions simultaneously in a clock cycle. So in modern processor, two or more instructions can be issued per machine cycle. So example of that is i960CA is a three-issue processor. Okay, next we have software parallelism. So software parallelism is defined by the control and data dependence of programs. So software parallelism is a function of algorithms, programming style, and compiler optimization. So the degree of parallelism is revealed in the program profile or in the program flow graph. So the program flow graph displays the patterns of simultaneously executable operations. So parallelism in a program varies during the execution period. So it limits the sustained performance of the processor. Okay, now let's see the mismatch between software and hardware parallelism. So what will happen if there is any mismatch? So for this example, or for case 1, we have 8 instructions. Okay, we have 4 load instructions and 4 arithmetic instructions, which consists of 2 multiplication operations, 1 addition, and 1 subtraction operations. So these instructions are to be, or these 8 instructions are to be executed in 3 consecutive machine cycles. So we have this A and B instructions. Okay, now let's take the first cycle. So in the first cycle, it's going to handle all 4 load operations. So we have L1, L2, L3, and L4. So after this, we're going to perform 2 multiplication operations. So we have your L1 into L2, and we have L3 into L4. Okay, so again, in the next cycle, for the third cycle, naman, which will be we're going to perform one addition and one subtraction operations. So we have L1 into L2. So we have L1 into L2 plus L3 into L4, which will give us the first instruction A. So this one, L1 into L2 plus L3 into L4. Okay, so for subtraction operation, we have L1 into L2, which is your x1, into L3 into L4, which is your x2. So this will give us the second instruction, which is instruction B. So L1 into L2 minus L3 into L4. So again, these 8 instructions are to be executed into 3 consecutive machine cycles. So we have 4 load instructions. In the next cycle, or the second cycle, we have 2 multiplication operations. And in the third cycle, we have 1 addition and 1 subtraction operations. So that it is, or so the total is 8 instructions and 3 cycles. So we have 8 instructions divided by 3 cycles, it is 2.67 instructions per cycle. So this is executing 2.67 instructions per cycle in this example. Okay, now let's proceed to the hardware parallelism using the same program. So in the first case, kanina, sa software parallelism, there are 8 instructions were executed in 3 consecutive machine cycles. So in hardware parallelism, the execution of the same program is by 2 issue processors, or 2 issue processors can execute either one memory access. So it can either load or write. So let's say if you want to load the data, then you have to get it from the memory. And if you want to store the data, then you have to write into the memory. And one arithmetic operator. So it could be addition, subtraction, or multiplication, and so on. So again, two issue processor means it can either support one memory access and one arithmetic access simultaneously. So with this hardware restriction now, the processor can handle again 2 issue process. So the program must execute in 7 cycles. So we have cycle 1, 2, 3, 4, 5, 6, and 7. So kanina 3 cycles lang to. So same program lang yapon. We have instruction A and B. So let's proceed na. Okay, so for the first cycle, so since we cannot perform 2 memory access at the same time, no, we may just want to load L1 first and then L2, so we can proceed to the next cycle. So we have L1 for cycle 1 and L2 for cycle 2. So next, after loading L1 and L2, we can now perform multiplication operation in cycle 3. So L1 into L2. So we have x1 for the first multiplication operation. So we can still load or do one memory access for this cycle. So nanatay one arithmetic, which is your first multiplication, and we can still do one memory access. So we're going to load L3. Now let's proceed to the fourth cycle. So since L3 is already loaded, we can only now load the L4. Okay. So for cycle 5, we can now perform the next multiplication for L3 and L4 since loaded naman silang duha. So we have x2. So this is L3 into L4. That's for that is for cycle 4. I mean that is for cycle 5, sorry. So for the next cycle, or for the cycles, for the sixth cycle, since we have already performed all the load operations as well as all the multiplication operations, we can now proceed to the addition. So since there is no need to load any, or there is no need to do any load access, so now we have L1 into L2 plus L3 into L4. So this will give us the first instruction A. This one. So L1 into L2 plus L3 into L4. Now for the last cycle, for the seventh cycle, we're going to perform the last arithmetic operation, which is subtraction. Okay, so we have L1 into L2 minus L3 into L4. So this will give us the second instruction, which is instruction B. So we have L1 into L2 minus L3 into L4. So by using the 2 issue processor hardware type, the same instruction sa case 1 kanina is executed in 7 machine cycles. So this will give us 1.14 instructions per cycle, since 8 instructions divided by 7 machine cycles. So whereas in the first case, sa software parallelism, the average is 2.67 instructions per cycle. So in this example, for hardware parallelism, we have 1.14 instructions per cycle. So this is the mismatch between the hardware and the software parallelism. Okay. That's it for the 2 types of parallelism. So for our reference, we have Database Systems Concept 6th edition. Thank you, everyone. Thank you, classmates. Thank you, sir, for listening. God bless po.